Welcome to our comprehensive exploration of wave optics. In this chapter, we'll uncover the fascinating behaviors of light when it's treated as a wave, rather than just a stream of particles. From the basic definitions to the intricate phenomena like interference, diffraction, and polarization, wave optics helps us understand a wide range of optical effects. We'll also see how these principles are applied in real-world instruments and technology. Let's begin our journey by laying the foundation with some essential concepts and definitions. Wavefront is a crucial concept in wave optics. Imagine dropping a stone into a calm pond. The ripples that spread out are similar to wavefronts. In optics, a wavefront is an imaginary surface connecting points of a wave that vibrate in unison. All points on a wavefront have the same phase. This concept helps us visualize how light travels and interacts with obstacles. Understanding wavefronts is the first step in grasping more complex phenomena like reflection, refraction, and interference. Huygens' principle is a foundational idea in wave optics. It states that every point on a wavefront acts as a source of tiny secondary wavelets, which spread out in all directions at the same speed as the original wave. The new position of the wavefront is found by drawing a surface tangent to these secondary wavelets. This principle not only explains how waves propagate but also lays the groundwork for understanding reflection, refraction, and other wave phenomena. See how Huygens' principle helps us derive the laws of reflection. When a wavefront strikes a reflective surface, each point on the wavefront generates secondary wavelets. The reflected wavefront is formed by drawing a tangent to these wavelets. This construction shows that the angle of incidence equals the angle of reflection, matching what we observe in everyday mirrors. Huygens' approach provides a clear visual explanation for this fundamental law of optics. Now let's apply Huygens' principle to refraction. When a wavefront passes from one medium to another, such as air to glass, the speed of light changes. Each point on the wavefront still acts as a source of secondary wavelets, but these wavelets travel at different speeds in the new medium. By constructing the new wavefront, we can derive Snell's law, which relates the angles of incidence and refraction to the speeds of light in the two media. This elegantly explains why light bends when entering water or glass. Interference is a striking phenomenon where two or more light waves overlap, resulting in regions of increased or decreased brightness. When the crests and troughs of the waves align perfectly, they reinforce each other, creating bright fringes. When they are out of phase, they cancel each other, producing dark fringes. This effect is a direct consequence of the wave nature of light and is essential for understanding patterns seen in experiments like Young's double slit. Destructive interference occurs when two light waves meet in such a way that their crests coincide, amplifying the resulting light intensity. For constructive interference, the path difference between the two waves must be an integer multiple of the wavelength. This means the waves are in phase and the resulting bright fringe is observed. This principle is key to understanding the bright bands and interference patterns. Destructive interference happens when two light waves meet such that the crest of one coincides with the trough of the other. This causes the waves to cancel each other out, resulting in a dark fringe. The condition for destructive interference is that the path difference between the waves is an odd multiple of half the wavelength. This explains the dark bands seen in interference experiments. Young's double slit experiment is a classic demonstration of light's wave nature. In this setup, light passes through two closely spaced slits and forms an interference pattern of bright and dark fringes on a screen. The experiment provides direct evidence of interference and allows us to measure the wavelength of light. It's a foundational experiment in wave optics and has influenced our understanding of light for centuries. Fringe width in Young's double slit experiment refers to the distance between two consecutive bright or dark fringes. It can be derived using the geometry of the setup and the conditions for constructive and destructive interference. The expression for fringe width is given by beta equals lambda d/d, where lambda is the wavelength of light, d is the distance to the screen, and d is the separation between the slits. This formula helps us predict and analyze interference pattern. Diffraction is another remarkable wave phenomenon. It occurs when light bends around the edges of an obstacle or aperture, spreading out as it passes through. This effect is most noticeable when the size of the obstacle or opening is comparable to the wavelength of light. Diffraction explains why shadows are not perfectly sharp and why we see patterns when light passes through small openings. Single-slit diffraction occurs when light passes through a narrow slit and spreads out, forming a pattern of bright and dark bands on a screen. The central maximum is the brightest and widest, with alternating dark and less bright fringes on either side. This pattern results from the interference of light waves emerging from different parts of the slit, demonstrating the wave nature of light. Angular width of the central maximum in single-slit diffraction is an important measure. It tells us how wide the brightest part of the pattern is. The width depends on the wavelength of light and the width of the slit. The formula for angular width is theta equals 2 lambda/a, where lambda is the wavelength and a is the slit width. This relationship helps us design experiments and optical devices with precise control over light pattern. Resolving power is a measure of an optical instrument's ability to distinguish between two closely spaced objects. High resolving power means the instrument can separate fine details, which is crucial in microscopes and telescopes. This property depends on the wavelength of light and the design of the instrument. Understanding resolving power helps us improve the performance of scientific tools and advance research. Resolving power of a microscope determines how closely two points can be distinguished as separate. It is given by the formula Rp equals 1d equals 2 mu sin theta/lambda, where mu is the refractive index, theta is the half angle of the cone of light, and lambda is the wavelength. A higher numerical aperture and shorter wavelength improve resolution, allowing us to see finer details in microscopic samples. Telescopes' resolving power is the ability to distinguish between two distant stars or objects. The expression is Rp equals d/1, 22 lambda, where d is the diameter of the objective lens or mirror, and lambda is the wavelength of light. Larger telescopes with bigger objectives can resolve finer details in astronomical observations, helping us explore the universe with greater clarity. Polarization is a unique property of transverse waves like light. It refers to the orientation of the oscillations of the electric field in a light wave. Unpolarized light has oscillations in all directions perpendicular to the direction of travel, while polarized light oscillates in just one direction. Polarization reveals the transverse nature of light and has many practical applications. There are several methods to produce polarized light. The most common include passing light through a polarizing filter, reflection from nonmetallic surfaces, and scattering by small particles. Each method selectively blocks or transmits certain orientations of the electric field, resulting in polarized light. These techniques are widely used in photography, sunglasses, and scientific instruments. Brewster's law describes the angle at which light reflected from a surface is perfectly polarized. When unpolarized light strikes a surface at the Brewster angle, the reflected and refracted rays are perpendicular, and the reflected light is completely polarized. The law is given by tan theta b equals n2 n1, where theta b is the Brewster angle and n1 and 2 are refractive indices. This principle is important in optics and photography. Polarization has many practical uses. Polarized sunglasses reduce glare by blocking horizontally polarized light. In photography, polarizing filters enhance contrast and reduce reflections. Polarization is also used in LCD screens, stress analysis of transparent materials, and even in 3D movies. These applications highlight the importance of understanding and controlling light's polarization. Wave nature of light is fundamental to modern optics. It explains phenomena like interference, diffraction, and polarization, which cannot be understood by treating light as just particles. Recognizing light's wave behavior has led to advances in technology, from microscopes and telescopes to fiber optics and lasers. This understanding forms the basis for much of today's optical science and engineering. Wavefronts can take different shapes depending on the source of light. Spherical wavefronts originate from point sources, plane wavefronts from distant sources, and cylindrical wavefronts from line sources. Each type helps us analyze how light propagates and interacts with objects, providing a foundation for understanding more complex optical phenomena. According to Huygens' principle, every point on a wavefront acts as a source of secondary wavelets. These wavelets spread out in all directions and their envelope forms the new wavefront. This concept is essential for visualizing how waves propagate and interact with obstacles, leading to effects like reflection and refraction. Constructing new wavefronts using Huygens' principle involves drawing tangents to the secondary wavelets. This geometric approach helps us predict the direction and shape of reflected and refracted waves. It's a powerful tool for analyzing complex optical systems and understanding the behavior of light in various scenarios. Snell's law describes how light bends when passing from one medium to another. Using Huygens' principle, we see that the change in speed causes the wavefront to change direction. The ratio of the sines of the angles of incidence and refraction equals the ratio of the speeds in the two media. This law is fundamental in optics and explains everyday phenomena like the bending of a straw in water. Superposition principle states that when two or more waves overlap, the resulting displacement is the sum of the individual displacements. This principle is at the heart of interference and diffraction phenomena. It explains how light waves can combine to produce patterns of brightness and darkness, depending on their relative phases. Path difference is the difference in distance traveled by two waves before they meet. In interference, the path difference determines whether the waves will constructively or destructively interfere. Integer multiples of the wavelength lead to constructive interference, while odd multiples of half the wavelength cause destructive interference. This concept is crucial for predicting and analyzing interference patterns. Coherent sources are essential for producing clear interference patterns. Two sources are coherent if they emit waves with a constant phase difference and the same frequency. Lasers are a common example of coherent light sources. In experiments like Young's double slit, coherence ensures stable and visible interference fringes. Intensity of light in an interference pattern varies depending on the phase relationship between the waves. Where constructive interference occurs, the intensity is maximum, resulting in bright fringes. Where destructive interference happens, the intensity drops to zero, creating dark fringes. This variation in intensity forms the characteristic pattern seen in interference experiments. Several factors affect the spacing of fringes in interference patterns. The wavelength of light, the distance between the slits, and the distance to the screen all play a role. Increasing the wavelength or the screen distance increases fringe spacing, while increasing slit separation decreases it. Understanding these factors helps in designing experiments and interpreting results. While both diffraction and interference involve the superposition of waves, they differ in their setups and effects. Interference typically involves two or more sources like in Young's experiment, while diffraction occurs when waves encounter obstacles or slits. Both phenomena produce patterns of light and dark, but diffraction patterns are often broader and more complex. In single-slit diffraction, the central maximum is the brightest and widest part of the pattern. Its width depends on the wavelength of light and the width of the slit. The central maximum contains most of the light energy, with intensity decreasing in the side fringes. This feature is important for understanding the resolution limits of optical instruments. Dark bands or minima in a diffraction pattern occur where the light waves from different parts of the slit cancel each other out. The positions of these minima can be calculated using the condition a sin theta equals m lambda, where a is the slit width, theta is the angle, and m is an integer except 0. These minima define the boundaries of the bright fringes. Diffraction grating consists of many closely spaced slits, producing sharp and well-defined interference patterns. Gratings are used to separate light into its component wavelengths, making them essential in spectroscopy. The patterns produced are much more detailed than those from a single slit, allowing precise measurements of light properties. Rayleigh criterion defines the minimum separation at which two-point sources can be resolved by an optical instrument. According to this criterion, two sources are just resolved when the central maximum of one diffraction pattern coincides with the first minimum of the other. This sets a fundamental limit on the resolving power of optical devices. Numerical aperture NA is a key parameter in microscopes and other optical instruments. It measures the ability of a lens to gather light and resolve fine details. Higher NA means better resolution. NA depends on the refractive index of the medium and the angle of light collection. It's a crucial factor in designing high-performance optical systems. All optical instruments have limitations due to diffraction and the wave nature of light. These limitations affect the smallest details that can be resolved. Improving resolution requires larger apertures, shorter wavelengths, or advanced techniques like immersion lenses. Understanding these limits helps scientists push the boundaries of observation. Light can be polarized in different ways: linear, circular, or elliptical. Linear polarization means the electric field oscillates in a single plane. Circular and elliptical polarization involve more complex oscillation patterns. These types are used in various technologies, from communication systems to advanced imaging techniques. Alice's law quantifies how the intensity of polarized light changes as it passes through a polarizing filter. The transmitted intensity is proportional to the square of the cosine of the angle between the light's polarization direction and the filter axis. This law is fundamental in analyzing and designing optical systems involving polarized light. When sunlight passes through the atmosphere, it is scattered by air molecules. This scattering causes the sky to appear blue and also polarizes the light. Polarization by scattering is used in atmospheric studies and helps explain natural phenomena like the blue sky and red sunsets. When light reflects off non-metallic surfaces such as water or glass, it becomes partially polarized. The degree of polarization depends on the angle of incidence and the material. This effect is exploited in polarized sunglasses and photography to reduce glare and enhance image quality. Polarization is widely used in modern technology. LCD screens rely on polarized light to display images. Fiber optic communication uses polarization to increase data capacity. Even 3D movies use polarized glasses to create depth perception. These applications show how understanding polarization leads to technological innovation. Wave optics isn't just for laboratories, it's all around us. The colors in soap bubbles, the iridescence of peacock feathers, and the glare reduction in sunglasses all stem from wave phenomena like interference, diffraction, and polarization. Recognizing these effects in daily life deepens our appreciation for the science of light. Study of wave optics has led to major advances in science and technology. Lasers, fiber optics, holography, and advanced imaging techniques all rely on the principles of wave optics. These innovations have revolutionized communication, medicine, and entertainment, showing the power of understanding light as a wave. Summary: wave optics provides a deeper understanding of light's behavior, revealing phenomena that cannot be explained by particle theory alone. From interference and diffraction to polarization and resolving power, these concepts are essential for modern science and technology. By mastering wave optics, we unlock new possibilities in research, industry, and everyday life. Thank you for joining this journey through the wonders of wave optics.